and 7.4 and 7.5 are really just a lot of shortcut theorems. They're going to be theorems that give us properties that we're going to be able to use to write proportions and then solve for missing measures. And some of them are going to be shortcuts that you could get away with not knowing and do it the long way. And some of them are going to be shortcuts that if you don't learn, you won't be able to work the problem because there won't be a way to do it without the shortcut. Okay? So it's going to be really important. So we're just going to use some properties of our similar triangles, which remember, if they're similar, their angles are congruent and their sides are proportional. Okay? And so then we're going to apply what are called proportionality theorems. So I'm just going to go through a lot of theorems here. If you look at 7.4 notes, it's just one page, right? It says 4 theorems, but one of them is just really the converse of the other one. So there's really just 3 theorems that we're going to look at and an example of each one, okay? The first one, the triangle proportionality theorem. Here's what it says. If a line is parallel, and that's going to be the kicker for this theorem, you cannot use this shortcut unless you are confident that your line, or even if it's just a piece of a line, that line is parallel to the third side of the triangle. If it's parallel, then there's a shortcut you can use. So if it's parallel, that line is going to intersect the triangle and divide the sides proportionally. What that means is you can take the little side of AE, which is one side of the triangle. Normally, you could not compare that to a quadrilateral piece down here at the bottom. We talked about that yesterday, if you remember. Instead, we drew little triangle and big triangle, and we did side over side equals side over side. But if this line is parallel, then the shortcut is AE over EB will always be the same as AF over FC. So it splits the sides proportionally. The 2 pieces of one side will be proportional to the 2 pieces of the other side. Does that make sense? If it's not parallel, you cannot do that. You would have to redraw little triangle, big triangle, relabel, and then compare corresponding sides of the triangles. Does that make sense? Okay, so if you look at the example, they give you the picture, and the first thing you're looking at is, do you have what? Parallel lines. So in the big triangle, you do have a line that is parallel to this third side. You cannot compare the parallel sides. That is not what the theorem said. You cannot compare the parallel sides. I want to say that again. You can only compare the 2 sides that have been intersected. So that would mean 10 over 4. So 10 over 4 will be the same as, go back to where you started on the other side, 14 over x, and x would stand for US. So 14 over x. Okay, so part over part equals part over part if the line's parallel, and you can only compare the sides that have been intersected. Cross multiply, but if you want, you could reduce first to make your numbers smaller. This would be 5/2 equals 14 over x, if you want to, and then cross multiply. 5x equals 28, so what is x? 5 2/3? Okay, 5.6 would be 3/5. Okay, so is that what you said? Okay, I'm sorry. 5 3/5 or 5.6. Either one is fine because it's exact. Do not round. Just because you have that calculator, you can only use it to change it back into fractions for yourself unless it says to round. That's x. Is that what we're looking for? Yes. Actually, yes, because that's what US stood for. So we would say 5 3/5 or 5.6. Questions? Okay, here's what's going to be tricky when you get to the homework or the test. If they ask you to compare the third side, so let's say that maybe we're trying to look for this over here and this is y. Let me use a different color. So maybe I'm trying to find y, and maybe I know this is 10. You're going to have to go back and draw it and look at the old way that we did it last class period, small triangle to big triangle, because you cannot compare the parallel sides with this shortcut. So you would just simply redraw a little triangle, and this is 10, and I should probably pick a different number then. Let's say this is 12. So 10 and 12, and then you would do the big triangle, and this is what? 14, and this is y. And then you could write a proportion comparing those corresponding sides. Is everybody with me? Don't fall for what they're trying to get you to fall for if you're looking at the third sides, okay? Or if you don't know the lines are parallel. If you don't know the lines are parallel, you're going to go back and redraw big triangle, little triangle, compare corresponding sides. Okay, and I just made up the number 12, so that may not work out nice and pretty, so don't try to work it. Okay. That was our triangle proportionality theorem. The next theorem that you're going to see on your paper is the converse of that. The converse of the triangle proportionality theorem just simply says, look at the picture. Do we have a line parallel? Nope, but we can check and see if it's parallel by looking and seeing, are the sides split proportionally? So is AE over EB the same as AF over FC? If those are proportional, so that they reduce to the same fraction, then we can say the lines are parallel. So it's just going backwards. So you're going to plug it in and check. Instead of the equals, it'll be more like a question mark. Are these equal? Okay, so for example, this one, it says verify that the sides are parallel, that DE is parallel to BC. So again, pick one side. What would we write down as our fraction? We're checking to see, is 10 over 15, is that the same as 8 over 12? And then you'll reduce and you'll show your work. So what's 10 over 15? 2/3. What's 8 over 12? 4 goes into both, 2/3. Good. And so those are equal. So therefore you can say that DE is parallel to BC. Does that make sense? Okay, so triangle proportionality theorem and the converse, pretty easy. It's just tricky if you aren't careful about the parallel marking. So they have to be parallel before you can use it, and it's only the sides that are intersected that are proportional. Otherwise, redraw small triangle, big triangle, okay? All right, the next one that you'll see on there is called the two transversal proportionality. That is basically going to say you have two transversals in your picture. If you have 3 or more lines, though, you can have 3, you could have 4, you could have 10, it doesn't matter. Those lines need to be parallel. So in the picture, if you have 3 or more parallel lines, they do not mark them parallel, they would need to be marked parallel. So you may want to add that to your notes. If 3 or more parallel lines are intersected by 2 transversals, then when they intersect those, they will divide the transversals proportionally. Okay, so that would mean AC over CE should be the same as BD over DE. Not really that I know of. It's just more writing those fractions out and like name them. I don't know any like markings. I mean, you can do whatever makes sense to you for your picture, but there's not anything that I've ever been taught. Is everybody with me here though? It's the transversals that are split proportionally. So it's this line segments that are in that picture will be proportional. It does not have to form a triangle. I mean, those could be straight up and down and never cross. But it just has to be 3 parallel lines or more and 2 transversals so that you end up with at least 4 segments, and then those segments are split proportionally. Okay, so again, if you look at this example here, this one's more of an application problem, and they're going to make you assume that those trees, which is very highly unlikely, but that those trees are perpendicular to the ground so that they are parallel to each other. Okay? More than likely with wind and the factors of the environment, those trees are not perfectly perpendicular and they're not perfectly parallel, right? So more than likely that's not really true, but pretend it is, and we'll assume here that these lines are all parallel to each other. So we have 3 or more parallel lines, right? And then we have those intersected by those dotted lines, which would be our transversals. So that means that any piece on this transversal compared to another piece on that transversal will be proportional to the corresponding pieces on the other transversal. Okay, and they want us to find LM and MN. That's our goal. They gave you the information, but they also already labeled it in the picture. So we could read through all that, but it's already in the picture for us. Okay, so if I want to find LM, I'm going to put an X there, and I want to find MN, so I'll put, oops. That one's x, this one's y. I said it backwards. Everybody with me what we're looking for? Okay, so we need to write a proportion to find those. Pick one transversal, pick two pieces that you know. Pick another transversal, pick two pieces where you have one variable. So what do we want to write down here? Okay, so what would I write down? AB over CB is equal to KL over LM or ML, doesn't matter, yes. So we are saying basically that 4.5 over 2.6 has to be equal to 4.9 over y. So everybody follow me there? The two pieces of the transversal on top should be proportional to the two pieces of the transversal on bottom. And they just have to correspond, make sure they're in the same location. Cross multiply and solve. And so if you remember day one, I said we're going to cross multiply a lot. You're going to cross multiply a lot today. So we have 4.5y equals what? 12.74. And then we'll divide by 4.5. So what is y? Okay, and what did the direction tell us to do? Nearest tenth. So what is that to the nearest tenth? 2.8? 2.8 what? Inches. Okay, so make sure that you round appropriate to the directions and include your units always. Slow down just a second. Is everybody with me here? Questions? No questions? Everybody got it? Okay, so now what do we need to find? MN, which we called X, right? I'll use our red marker here. Okay, so what are we going to do different than for this one? Go ahead, Alexis. Okay, so BC over CD. Okay, so I'm going to warn you, the only reason I wouldn't do that is because do we know the exact value of LM? We actually had a rounded answer, right? We could use that long decimal calculator, but it's better to use an exact value and not a rounded answer. And the other reason I wouldn't do it is because what if you made a mistake finding y? Then what's going to happen when you find x? It's going to get that wrong too. If you go back to what was already given to you, then you won't have as, if you do end up missing y, then maybe you won't miss x. Okay? So what could we do instead? Oops. Tell me again, Tyler. Be specific. Okay, so you're saying instead of doing CB, we're going to do CD? But he was already using CD. He said BC over CD equals LM over MN. Exactly. Very good, Alexis. So you can do AB over CD. That's what you meant. Okay. I got you, Tyler. And that should equal KL over MN. Okay, so pieces of those transversals on top should be proportional to the pieces of the transversal on the bottom. Okay, so let's write that down. So I'm going to have AB over CD equals KL over MN. All right, so Tyler, fill it in with numbers for us.
4.5 over 4.1 and 4.9 over x.
Very good. And then we're going to, once again, cross multiply and solve. So we have 4.5x equals what? 20.09. And then what do we do? Divide by 4.5. And what do we get for x according to the directions rounded correctly? Okay, so Alexis gave us the calculator, but what do we get total when we round according to the directions? 4.5 what? Inches. All right, so we were looking for MN. So MN is 4.5 inches. All right, questions on the two transversals proportionality? And all of them will be until you put it all together on the homework, and then you've got to decipher which theorem do I use, what is my picture showing me. But the big idea of each one is really not hard. Okay? All right, we have one more left on this one, right? And it's also just as easy. Just as easy. Sorry, this goes through so much explanation. Okay, so the last one, triangle angle bisector theorem. So obviously, what are you going to have a picture of? A triangle. What's going to happen inside that triangle? Okay, what's going to get bisected? An angle, okay? Triangle angle bisector theorem. So it is, that's right. It's getting bisected, but one angle is getting bisected, right? If you have a triangle and the angle is bisected, then it's going to split the opposite side. So if it splits this angle, the side that it intersects is going to get split proportional to the other two sides. So in other words, BD over DC will be the same as, here's the kicker, you started with B, do not jump over here. It will be equal to BA over CA. So make sure that where you start is consistent. So in other words, I'll make up one just real quick here. So let's say that this is X, Y, W, Z. Okay? I don't know. So let's do our proportion here, just using variables. So what would I have? X over Y equals W over Z. Are you with me? What you cannot do is X over Y equals Z over W. And that's what I see often because you were on that side of the triangle and you want to just keep going with that side of the triangle. Okay, but you can't do that. If you start on the left, X over Y, then go back to the left, W over Z. Okay, so that's your last one in 7-4. If you look at this example, again, you're looking to see, do I have a triangle? Do I have an angle that's been bisected? Yes, so now we're going to write a proportion and then just cross multiply and solve. So what will my proportion be? Over, good, equals, very good. And again, if you don't want to work with those big numbers, 40 over 32 will reduce. What goes into 40 and 32? 8. Goes in there how many times? 5. Over 4. So you don't have to do that, but if you don't want those giant numbers, it makes it easier. Just don't forget you can't cross cancel with an equal sign, but you can reduce a fraction that's on one side. So I'm going to reduce it just so I can work with some smaller numbers and then cross multiply. So 4 times x plus 5 equals 5 times x minus 2. Don't forget to distribute. You should get 4x plus 20 equals 5x minus 10. Did I lose anybody there? Okay. And then from there, you can subtract your 4x. And so we have 20 equals x minus 10, and then add 10. So x is equal to 30. But that is not what it asked us to find. What did it ask us to find? PS and SR. So go back and plug it in. PS then will be 30 minus 2, which is 28. And SR will be 30 plus 5, which is 35. No line segments over PS and SR. Last night in my other pre-AP classes, when I was grading homework, I wrote on at least half of their homework assignment, no line segments. Exclamation point. No, not yet, because I'm trying to get them better. Tests, I will. Okay. Probably at this point, I'm about to take off on homework if I haven't already, but on tests is when I usually take off. So I warn you on homework over and over again. Spelling, punctuation, all the little things, and then test day, I take it off. If they're congruent, you put a line segment. If you're just telling me what it's equal to, then no line segment. Distance, numbers, no line segment. Okay?
If you have numbers, if you don't put a line.
Correct. Okay, any questions on 7-4? Would you agree pretty easy? Just 3 theorems really? One of them was the converse of the other one and then 2 other ones? So there was our triangle proportionality theorem.
And then the converse.
Converse of the triangle proportionality theorem. That was about the line being parallel. Then there was the 2 transversal proportionality theorem. So that's going to be parallel lines cut by 2 transversals. And then your triangle angle bisector theorem. triangle with an angle bisector. You won't use those as much in proofs, so it's going to be more so that you need to know how to use it in a picture. I think the two transversal proportionality theorem may come up like they may ask you, is this the converse or not the converse? But other than that, it's more just can you apply it to a picture. Okay, so this is where we're actually going to make scale drawings. So you will need a ruler for this lesson. So if you don't have one, jump up and grab one real quick. Grab one real quick.
Oh my
Oh, you could have. Fine. Yeah.
Don't care to eat.
No, it's not what I said.
Oh.
He thought it said don't care, be evil. Yes, Elena looks like the kind of person that's just evil.
Sorry.
All right, so indirect measurement. How many of you have been setting up on the third floor and looked at, has anybody been on the third floor?
Never been on the third floor.
Man, not as much now because they moved Summit up there, so we don't have as many classes. Okay, so not on the third floor. How many of you have ever been in a second story or third story room and you looked out the window and you thought to yourself, I wonder how tall that flagpole is? I wonder how tall that telephone pole is?
I wonder if it would hurt if I jumped
So, obviously, no, you're not. Okay, so if you ever have that thought, I want to know how tall, maybe you're sitting on the third floor looking at the flagpole outside, or maybe you just walk outside today and you're like, I do wonder how tall that flagpole is. So, when you cannot physically measure something, because it's too high, too far away, whatever, you can use what's called indirect measurement. Indirect measurement is any method that uses formulas, distance, midpoint, similar figures, which is what this lesson's all about, and or proportions to measure that object. So we could measure the height of that flagpole outside, and we're going to talk about an example just like it in a minute. If we went out there on a sunny day where the sun was casting shadows, if we knew our own height, which I know my height, could go out there, I could stand parallel to that flagpole, and I could get the distance of the flagpole shadow, because the shadows land where? On the ground, right? So I can measure the ground, I just can't measure high up in the air, right? So I could get the distance of the flagpole shadow, I could get my shadow, maybe with some help, because if I try to walk to the end of my shadow, what's happening? It's moving. So I'd have to be really good at my tape measure, or I'd have to get someone to help me. But I could measure my shadow, and I know my height, so then I could figure out the height of the flagpole by writing a proportion. Okay? So we can find the measurements of objects that we can't physically measure by indirectly using similar figures. And me and the flagpole would make similar triangles because the angles cast from the sun would be congruent going down. And I would make a right angle with the ground, and hopefully the flagpole's making a right angle with the ground. Yeah, you could do that too. All right. We talked about this the other day when we were doing the car model. With me? When we were doing the car model problem, that you can have different units in a proportion, right? You could have meters on top and centimeters on bottom, but they need to be consistent. So in that one shape, if it's measured in meters, it's all measured in meters, and in the other shape, it's all measured in centimeters. But you cannot, if I were out there measuring the flagpole, I could not measure my measurement as 5 feet 7 inches, because that's in feet and inches. You have to convert to one or the other. So I would either need to say 5 feet and 7 out of 12 inches, or I would need to convert that to 67 inches.
67 inches looks better.
Okay? So you would either do feet or you would do inches, but you can't have both in the same problem. All right. Probably. Yeah. Okay. So here is an example where Tyler
Tyler.
wants to find the height of a telephone pole. He measured the pole's shadow and his own shadow, and then he made a diagram. So again, if that sun's shining down, we've got shadows, we've got these angles are going to be congruent from where the sun is. So if we're standing parallel to it. Sorry, Tyler, they just picked on you here, but
Correct.
all right. So do you guys want to work with fractional feet or do you want to work with whole number inches? Okay. So let's convert all these real quick. What is 5 foot 9 inches going to be? 69 inches. What is 7 feet 8 inches going to be? So we do 7 times 12 plus 8. Everybody agrees that's 92 inches? Okay, make sure we don't make a mistake anywhere. 38 feet 4 inches, we're going to have to do 38 times 12 plus 4. Okay, so 460, I'm hearing from several of you, inches. So when you get to the homework, make sure you convert from one or the other. However, if it says to give the height, your answer should be how you would actually tell someone. You don't go up to someone and say, I'm 69 inches. You don't do that. So don't do that, okay? Right? That's like moms that come up and say, my baby is 35 months old. We don't do that anymore once we're past a few months. Like you start saying a year, 2 years, you don't say 35 months. So, yeah, and you wouldn't quote your age like that. Golly, that would be bad for me. I'm not doing that. Okay. So make sure you go back in your final answer and convert it back to feet and inches, okay? And if you need help with that, I'll help you. So we want to work this problem using the idea of indirect measurement. Again, do you guys understand why the triangles are similar?
Yeah.
Angle similarity here. We have right angles, and then we have the shadow that the sun is making. Those angles are going to be congruent as well. So now we can just write our proportion. So we would have 69 over 92, sure, equals h over 460. Cross multiply, we know our units are going to be in inches because everything is in inches right now. So we have 92h equals, what's 69 times 460?
That's a big number.
31740. So 31,740. Okay. And then we're going to take that and divide it by 92. And so what is the height in inches right now? 345 inches. Okay. It didn't say how to leave your answer, but I'm telling you, I want you to convert that back to feet and inches. So go ahead and change that. That would be equal to, how do we change it?
28
And between 7.
divided by 12.
Okay, so I want to make sure you can do this for the ones that don't turn out to be nice, pretty 0.75, okay? Because it may be something like 0.83333 or 0.26154. So you would do 345 and divide it by 12, and that goes in there how many times? 28, and if you used your calculator to do that, that's fine, but it's going to tell you 28.75, right? And if this number is not an exact decimal that stops and it keeps going, you would be better off to go ahead and do 28 times 12 on your calculator. And what is 28 times 12?
Equals 336.
336.
And then you would just put that
And then subtract, and what do we get here?
1.
9. So that means it's going to be 28 feet and 9 out of 12 inches, which is just 9 inches. Now, what if it had been, let's say, 2 out of 3?
Just make it
Then we would multiply it by 12 to get how many inches that is. So if I multiply by, because it's 2/3 of a foot, so 2/3 times 12 is, yes, 8. Okay, so whatever you get here as your fraction, 9/12, we just multiply it by 12 to get 9, or 2/3 multiply it by 12 to get how many inches, because this is how much of a foot you have. Does that make sense? Okay, so let's do one more. Let's say I had, but I want you to write it in feet and inches. Okay, so if you have, let's say, 214 inches, just making up a number. Okay, so what are we going to do to get it into feet? Divide by 12. So what do we end up with? Okay, so 17 something. So go back, take 214, you're dividing it by 12. You know it goes in there 17 times. What's 17 times 12? Okay, 204. We subtract, we get 10. That's 10 out of 12 feet. So you multiply it by 12 to get how many inches, and it's 17 feet, 10 inches.
Okay, so stay with like the one under.
Say it again, Tyler.
Fractions.
Mhm. Does that make sense, Katrina?
It'd be amazing.
Cindy, we good? Good over here?
If you wouldn't, you can fit in a building.
All right.
Or small.
So
You'd have to like take down and call it.
28 feet 9 inches is the height of the telephone pole. Tyler doesn't have to wonder anymore.
Yeah, Tyler.
Glad we can pick on you, Tyler. All right.
Somebody trying to find it.
You want me to pick on you, Edwin?
No. I get pissed off and speak. So now I was supposed to say speak. I was pissed off.
That's
There was
awesome.
literally a marker like across the hall, and she goes up to me, "Did you throw this marker?" And it wasn't even me.
So what you're telling me is your reputation is you're the kind of guy that would throw the marker across the room.
Oh, it's not me. She's thinking of.
Okay, scale drawings. So this is where you really physically will have to do some scale drawings on your homework and on the notes. A scale drawing is just simply represents an object as smaller or larger than its actual size. The drawing scale is going to be, and I want to make sure I'm clear here, scale is different than similarity ratio. Your scale can compare two different measurements and usually does. The scale is the ratio of any length in the drawing to the corresponding actual length. So for example, notice our scale here is 1 centimeter to 1,500 meters. It's like on a map, they give you the scale. Okay, so I'm just making sure you're clear. This is not, guys, make sure you're with me. This is not similarity ratio. On the test, if I say, what's the similarity ratio? Similarity ratio has to have the same units, and the units cancel out. So if I wanted to convert this, how many centimeters are in a, or how many meters are in, okay, we'll do centimeters. How many centimeters are in a meter? How many centimeters are in a meter? 100, okay, 100. So if we want to change this to centimeters, we would have to do 1,500 times 100, right? So this would become 1 centimeter compared to, if I multiply by 100, that's going to be 150,000 centimeters, right? So then what happens to the centimeters? They cancel out. So the similarity ratio is 1 to 150,000. This would be the similarity ratio. The scale is measured in different units, so this is the scale. So here's the thing, if on the homework they give you the similarity ratio and there's no units, that always confuses students. They're like, wait a minute, there's no units. How do we know what our units are? The units are whatever is in the picture. If it's 1 to 150,000, then if your picture is about feet, it's 1 feet to 150,000 feet. If your picture or your problem is about miles, it's 1 mile to 150,000 miles. The units are the same if it's a similarity ratio. They've given you the units in the problem. The units cancel out. So whatever's in your problem are your units. Does that make sense? But a scale can compare different units. So if you have a scale and they say, what's the similarity ratio? It's not what your scale is. You'll have to convert it, and then that's your similarity ratio. Okay? All right. Making sure we're clear there. All right. So that basically says the same thing. So now we're going to figure out, so back in the day, way before GPS and having this maps on your phone, if you're my husband who's a truck driver, he says, oh, that Googling the GPS, it just gets you on some dirt road somewhere, use a map. And so he's old school. He likes his hard copy map. So he has these big maps he takes with him, and I'm like, because I've grown up in the day and age along with you where we have our GPS, and I go to all the ball games. I don't know where I'm going. I just always type in, El Dorado High School, and it takes me where I need to go, so I don't worry about it. So
Yeah.
back in the day, this is what this problem is going to ask you to think. Way back in the day. So on a Wisconsin road map, Kristen measured a distance of 11 1/8 inches from Madisol to Wausau. I don't know how you really say that. Okay? So she took the map and she said, I've got these two locations and I want to figure out how far apart they are. So she just said, with my ruler, I'm going to measure, and this is from Madison to Wausau, 11 1/8 inches. Okay? And she knows that according to the map, 1 inch is the same as 13 miles. So is that a scale or a similarity ratio? That's a scale, okay? And they ask, what is the actual distance between these two locations? So she doesn't have a GPS. She only has this map. She wants to know how far is it going to be? How many miles am I going to have to drive to get from here to here? If it's 11 1/8 inches. So we're going to write a proportion. Start with your scale. 1 inch to 13 miles. We know that should equal the next fraction. Keep your units in the same location. So what's going to go on top? 11 1/8 inches. So if 1 inch is the same as 13 miles, then 11 1/8 inches should be the same as X. That's what we're trying to find. Okay, so we have our calculator, which will make this a little easier. Cross multiply, but before I do, what do we know our units are going to be in our final answer? Miles, because we're in the same location. But again, I'll show you if I were to multiply, I have 1 inch times X equals, and then I'm going to do 11 1/8 inches times 13 miles. And when I do that, and I divide by 1 inch, what happens to my inches? They cancel out, right? So I just want to remind you that that's why you can do different units in a proportion, because your units will cancel out. Okay? So it'll just be 11 1/8 times 13, and your answer will be miles. Yes, I'm just trying to make sure we understand why the units are canceling. And yes, you could have because of the 1, but this might be 5 1/3 inches in 13 miles. And so then you would have to write a proportion and cross multiply. Okay, so help me out. What is 11 1/8 times 13? And do you know how to type in fractions on a calculator?
Don't use like a
Okay,
special
you won't get to use that one though on the test. You'll have to use mine. So you may want to grab one to practice. Does everybody know how to type one in though on these? Okay, I'm going to get one and show you real quick since I'm letting you have a calculator. And then if you don't have one, you can jump up and grab one at the same time. And I'll show you real quick. Because you can do parentheses, but that gets harder. There is a place where you can type in fractions on here. And you get a calculator for the ACT, so the better you are at using it, the better you will be as far as how fast you need to be and so forth. Okay, so you go to second math, or excuse me, that's not right. You go to math. Just kidding. Give me a second. Okay, sorry. You go to alpha, y equals. So alpha is the little green key. Alpha, y equals. And then you have options of what you want to type in here. The first one is if you just want to type in a regular fraction. The second one is if you want to type in a mixed number. The third one is if you want to take an improper fraction and change it to a mixed number. And then the fourth one lets you go from fraction to decimal or vice versa. You can go back and forth between those. Okay? That's right. That's right. So I wouldn't let you have that. So what do we want to type in? The second one, we want to type in number 2. And we want to type in 11 1/8. So you're going to do 11. And then notice the little flashing arrow. So use your right arrow key over here to change. And then 1. And then again your right arrow key. And then 8. Okay, and then you're going to multiply that by 13, right? Is everybody with me? Okay, and then notice you get 1,157 over 8, and we want to change that to a mixed number, right? So go back to alpha, and then y equals. And which one lets us go from mixed number back to, or improper to mixed number? 3, and it'll go both directions. So if you want it improper, it'll change the other way as well.
100.
So number 3, enter 144 and 5/8. Okay, so where is all your fraction work at? What 2 buttons? Alpha, y equals. Okay, and that's where you can find all your fraction options to do whatever you want it to do. And so I don't want you to lose your fraction skills because come January, we're back to proficiency testing again. But I do want you to be able to know how to use your calculator for time purposes. Okay? Are we good? All right, moving on.
That's why I needed it.
So this is going to be 144 and was it 5/8? And what are my units? Oh, miles. And it said round to the nearest mile. So what's our answer? 145 miles. Okay. I just wanted to make sure I taught you how to use your calculator for those fractions.
Dude, when Javi's gonna listen to this, he's gonna listen to this.
Oh, I hit the wrong thing. Sorry. Okay. Is this our last example or do we have more?
We have
2 more of that. Okay, yeah, those are really important. Okay. So this is where you're going to create a scale drawing, and you will have questions just like this on your test. Okay, super important. We're going to have to pick up the pace a little bit here. We're going to run out of time. So Lady Liberty holds a tablet in her left hand. The tablet is 7.19 meters long and 4.14 meters wide. If you made a scale drawing using the scale of 1 centimeter to 0.75 meters, 1 centimeter to 0.75 meters. And I would warn you, don't try to do shortcuts because those numbers may not be 1 to something on your test. It could be a decimal to a decimal or a fraction to a fraction. Okay, create the scale drawing of what it would actually look like. So you have a tablet that is 7.19 meters long and 4.14 meters wide. And mine's not drawn to scale, obviously, there. We want to come up with what would the dimensions be for the actual tablet, and then we want to use our ruler and draw it. So, really quickly, how many times am I going to have to write a proportion here to find the dimensions? Twice. Once for the length and once for the width. So we'll do length first. Every time, start with your scale. 1 centimeter to 0.75 meters. Okay, we'll do length first, so we know that it was 7.19 meters. Where does that go in the fraction?
bottom.
Wherever the meters was before. Keep your units in the same location. So 7.19 meters on the bottom, X on the top, because we're trying to figure out how many centimeters should it be for our scale drawing. Cross multiply, you get 0.75x equals 7.19. And then divide by 0.75. And it says to round to the nearest tenth, so what would it be? 9.6. And what are our units?
Centimeters.
Centimeters, because remember that's the scale version. So we know the length is going to be 9.6 centimeters. Before we start drawing, let's find the width. So the width, we're going to do the same thing again, but now use the width. So again, for every dimension, you'll have to do a proportion. 1 centimeter to 0.75 meters is equal to what over, and this time it's 4.14 meters wide. Are we good? Okay, cross multiply. You get 0.75x equals 4.14 and divide by 0.75. Round to the nearest tenth. Somebody agree with Tyler? All right. So we have 5.5 and 9.6. So now you're going to take your ruler, and I'm going to do the same thing on the board. You're going to draw a rectangle with those dimensions for your tablet. So flip your notes over to the back where you have room. Those are approximate symbols. Barely they're squiggly, but it should be little approximation symbols. Okay, so make your scale drawing. Make sure you're using the centimeter side, not the inches side. Make the scale drawing of the tablet. And label your picture with your measurements. Oops. And then look at your drawing compared to my drawing. Do they look the same size? This is my most favorite thing. I'm going to model with yours.
What did I do wrong?
You didn't do anything right.
Are you sure?
Besides, you didn't label. Make sure you label.
Real quick.
So does your shape look the same size as mine?
No, we draw on a bigger board.
Right. And so it's that whole illusion of perception. If you take yours up there, notice it is the exact same size, right? So it's so cool. If I take Alexis's paper, over there it looks much bigger, but when I get it up here at the board, notice it is the exact same size as mine. It's perfect.
My lecture.
So I love that illusion where you're like, wait a minute, I know. Yes. Nope. Okay. I'm going to go quickly next because this stuff that's left in the notes is so important and you're going to see it on your test a lot and on your homework, and it's probably one of the harder parts there, so we need to talk about it.
Quit switching out.
I know. It's because my little arrow's there.
It's going. Don't be clicking, don't click.
I know.
Click. It's switching out. Whoa. I think that was bigger than ours.
Okay, so it's probably going to keep going, but this is where you want to be. I'll come back to it in a second. So flip over to the back there. It's probably going to end the whole thing here in a second. Stop. Stop. Yes, thank you. Okay, so where I want you at is on this part right here. So flip it back over so that you're in the bottom part, and I want us to talk about our similarity ratio compared to what we've learned so far. Okay, right here. So we've learned about oh, come on, Lashley. I got to move my mouse. That's the problem. My mouse is in the way, and so it's messing everything up. Okay, so move my mouse out of the way. So similarity ratio compares two sides of our triangle, and if our two triangles are similar, it's the number we get when we reduce. So the similarity ratio here is 1 to 2. Remember that whichever one you name first has to go on top. If we flipped the order, the ratio would become what? 2 over 1. If you flip it, then that means you have to flip the fraction because you're starting with the other number. Okay, so here's what you're going to learn, and I'm just going to tell it to you for time purposes. The ratio of the perimeters will be the same as the similarity ratio. So if you take the perimeter of the first one over the perimeter of the second one, you are going to get the same ratio. So write this down. The ratio of the perimeters is equal to the similarity ratio. That's the first thing you need to get from this chart. If two figures are similar, the ratio of their perimeters will equal the same as the similarity ratio. So side to side will be the same as perimeter to perimeter. Okay? Area of the ratio of the areas is different. The ratio of the areas will be the ratio of the perimeters squared. So write that down. The ratio of the ratios squared would be the same. So the ratio of the areas will equal the ratio of the perimeters squared, which is the same as the ratio of the sides squared. That's super important. Ratio of the areas is equal to the ratio of the perimeter squared, which is equal to the ratio of the sides squared. Okay, so I'm going to show you an example. And maybe more than one. But here's where that's listed in your notes. If the similarity ratio is A to B, then the ratio of the perimeters is also A to B. But the ratio of the areas is A squared to B squared. Okay? Or you can write it as A over B squared. Same thing. So here's how you're going to use that. They're going to give you a problem like this. This has a typo. Fix it real quick. This should say triangle LMN is similar to triangle QRT. So given that the two triangles are similar, they want you to find the perimeter and the area of the second triangle. They do not give you enough information in that second triangle to calculate perimeter or to calculate area. So what you're going to do is use these ratios to figure it out. So we said the ratio of the sides, so 13 over 9.1 should equal the ratio of the perimeters. So that would be 36 over x. And so we'll call the perimeter here x. The ratio of the sides, which is your similarity ratio, should equal the ratio of the perimeters. So set that up, cross multiply, and solve. What do you get? 13x equals 327.6. Somebody agree with Sarah? Okay, divide by 13. What do we get for the perimeter? 25.2 units? Centimeters. So the perimeter of triangle QRS would equal 25.2 centimeters. Do you follow what I mean by ratio of the sides is equal to the ratio of the perimeters? If they're similar. So side to side will be the same as perimeter to perimeter. Okay, here's the part that's trickier. Now we're going to try to find the area. So we can let area equal y here in my work. It is the ratio of the sides, 13 over 9.1 squared is equal to the ratio of the areas. So what's my area of my first triangle? Nope, area? 60 over y. Nope, the only thing you square are the sides. The ratio of the sides gets squared, and those are equal to the ratio of the areas. Or it could be the perimeters. We could have done the perimeters, perimeter to perimeter squared, because those are the same. Okay, so you're going to square both numbers here. 13 squared I know is 169. What's 9.1 squared? Say it again, Grant. 82.81 equals 60 over y. And then you just cross multiply. So 169y equals 82.81 times 60. Say it again, Edwin.
4,968.6.
Okay. We agree, Tyler?
Yeah.
And then divide by 169. So the area of triangle QRS is equal to 29.4 units, centimeters squared. And don't forget to square your area. Okay, so side to side is the same as perimeter to perimeter. Side to side squared is the same as area to area. Okay, what if they ask you to go backwards real quick before I hand you your assignment? What if they tell you the ratio of the areas is this? And they ask you for the ratio of the sides, or the similarity ratio. You just square root it. So remember, the ratio of the areas is a squared to b squared. And the ratio of the sides, or the similarity ratio, is just a to b. So it would be 3 over 4. Now, it could be these aren't nice, pretty numbers, and you have to simplify square roots. But do you get the idea? Just go backwards, take the square root. Because if they give you the ratio of the areas, they're giving you a squared to b squared. And if they ask you for the similarity ratio, or the ratio of the sides, it would be the square root of those. Okay?